Hello guys, welcome back to our second video of the F equals MA problem series. Here we will be continuing the 2019 A test with problems 4 through 6. So for the fourth problem, we have a massless spring hangs from the ceiling and a mass is hung from the bottom of it. This mass is supported so that the initial tension in the spring is 0. It is then suddenly released. At the bottom of its trajectory, the mass is 5 centimeters from its original position. Find the oscillation period. Now, this seems pretty basic at first, but then we soon see that there are some problems we had to take some creative measures to fix. Obviously, we know that period of a spring is equal to 2 pi root m over k, mass over spring constant. So we don't have mass. We do not have spring constant. All we know is that here is the ceiling, here is the spring, and here's a spring with a mass on it. At the bottom of its trajectory, it is 5 centimeter, which is 0.05 meters. This tells us that the equilibrium point is right here. And this is 2.5 centimeter equals 0.025 meters. So now we know that F equals kx But since we're looking at the equilibrium point right here, that means that the force pulling the spring down is ma, which is mg, because A is gravitational. So mg. Therefore, look, we have m and we have k. So we essentially can write this as m over k is equal to x over g. So now we have period equals 2 pi square root of x over g. Now x over g is equal to 0.025 meter over 10. Because in F equals ma, they say that we should take the gravitational constant of acceleration as just 10 meter per second squared. So we could calculate this right now. And we get 1/10 pi. And this is the same as basically 0.314, etc. And so we have t equals 0.314 seconds. And this is our answer. And as you can see, it is correct. Here's problem number 5. A cylinder has radius r and weight g. You try to roll it over a step of height h, which is less than r. What is the minimum force needed to roll the cylinder over? For this, let us start by drawing a diagram that is slightly bigger so we can actually draw on it. We have this step h. Here's the center of the cylinder. Now we have this length, which is r. This length is also r. So now we already know that this is basically a torque problem. We need to equate the torque of gravity with the torque of a moment arm that's large enough, that is the largest possible, so that we need to exert the smallest amount of force this way, in this direction. So that means essentially to find the torque exerted by gravity, we need this moment arm right here. And to find that, we're going to have to use Pythagoras theorem, because we know that right here is h, right? This is going to be r minus h. And we'll call this x. So to equate the torque, essentially we have the torque equals xg, because g is the weight, which is a force, and it's pointing downward, so it's perfectly perpendicular with the moment arm. This is going to be equal to the largest moment arm possible, which is 2r, multiplied by f. So now let's actually calculate this thing. To find x, we just use Pythagoras theorem. It's going to be r squared minus r minus h squared. And this is going to yield r squared minus 2. Yeah, and now we can get some things to cancel. Since we have this negative sign, we can distribute it, and we find that these r squared goes away. This plus turns to a minus, and this minus turns to a plus. So now we have a result as square root of 2hr minus h squared. This is equal to x. Now we can finally use this torque balancing equation. So we have g times 2hr minus h squared is equal to 2r times f. And we just want to find f. That means we just bring this to the denominator, and we get g root 2hr minus h squared divided by 2r equal to f. And we can clearly see that this is the same as answer C. And yep, that is our correct answer. Now we can move on to our sixth and final problem for this video. A ball is released from rest above an inclined plane and bounces elastically down the plane. As the ball progresses down the plane, the time and distance between each collision will be A, remain the same and increase, B, increase and remain the same, C, decrease and increase, D, decrease and remain the same, and E, both remain the same. So first, let's start by drawing our diagram. We have an inclined plane of some angle theta, we have a ball that's dropped from here. And so its trajectory is gonna be like, and it's gonna bounce. And some of its energy is going to, potential energy is going to be converted to kinetic energy. So it's gonna bounce further the next time, and on and on. So this is more of like a concept problem. Let us show the plane like this, where this is theta. We can see that the gravitational acceleration that is acting downward is going to be equal to g cos theta. And since we're dealing with our, essentially our y component of acceleration being constant, this means that our t is also constant. So time remains same. So now we can eliminate some things. And already we see that like we only have A, or we only have E and A left. So now we need to figure out how will the distance change, or how will it react. Well, for the distance, remember that there is still a component in the direction of the plane going in the x direction, not the y. That looks like this. We have theta, the ball is bouncing with gravitation acting constantly downwards at g cos theta. And in this direction, we have g sine theta. Yeah, and since g sine theta is accelerating in the x direction by v equals u plus at, or v0, and distance equals v0t plus 1/2 at squared. We know for sure that as time goes on and the ball keeps bouncing, the distance that it crosses is going to increase. And hence we know distance increases. And so that cancels our choice E, and hence choice A is correct.